Hi, and welcome to Group 5's presentation on differential geometry. Differential geometry is a branch of mathematics that looks at geometry of curves and surfaces. It's used to visualize and understand shapes of curvatures on geometric objects. It has developed a lot over the years, dating back to the 14th century, when École d'Oresme made first attempts at studying curvature within plane curves. Other notable figures had a hand in its development, including Newton and Leibniz. Leibniz attempting a first definition in 1684. Ideas such as arc length and curvature radius came about. Later on in 1771, Mond developed the idea of space curves, with Cauchy giving definitions for curvature and torsion that are still used today, and the idea of moving frames came about by Darboux. The development in the study of surfaces came about with contributions from people such as Euler, giving the first notion of surface curvature in 1767, having previously theorized about it as early as 1748. Gauss introduced Gaussian curvature in 1828, understanding the importance of parametrization, and also Sophie Germain, mean curvature. Applications of this field of study include image processing, Einstein's theory of relativity, with curvature of space-time, and also positioning of satellites.
So firstly, we will have a look at plane curves. A plane curve is a curve that lies in a singular plane, i.e. in 2D. For ease, we will only be looking at curves that are smooth, which means curves that are parameterized and always differentiable, as we will always be looking to find the tangent. Some examples of smooth curves are a parabola, a hyperbola, and a circle. So, what defines a plane curve? Well, there are many attributes that help us understand what a plane curve is and how it is shaped. Firstly, we must look at the length and the arc length function of a curve. The length of a curve between points A and B is the integral of the length of the tangent, whereas the arc length function gives us an explicit equation for the length, in which you plug in t and t0 to get the length between 2 points. A curve is defined to be regular if the speed of the particle at time t is never zero, i.e. it is never flat, at any point and is always increasing or decreasing. A very simple example of this is the line y equals 3, as shown in the graph. A curve is unit speed if the speed of the particle is 1 for all t. All regular curves can be reparameterized to unit speed by the following steps. You check to see if the curve is regular. You compute the arc length function and its inverse and reassign this to equal a new function phi and redefine the range accordingly. You then find the new reparameterized curve to be our original curve composed with phi. This curve will have unit speed, thus being a unit speed curve. We then have the curvature and the sine curvature given by the following formulae. The curvature tells you how much the tangent rotates along the curve. The sine curvature tells you whether the tangent is curving positively or negatively. This gives light to the fundamental theorem of plane curves, that if you have a constant k, there exists a curve with sine curvature equal to thus k. A Frenet frame is a 90-degree frame that is composed of the normal and the tangent for each point t on the curve. Thus, it is known as a moving frame along the curve, making it an orthonormal basis of the plane. The plane curve we have been given to study is the curve shown. The curve is regular for all points t except when t equals 0. Thus we restrict t to be greater than 0 so we can proceed with our calculations. The curve is not unit speed, as the speed of the tangent does not equal 1 for all t, and we cannot reparameterize it to be unit speed explicitly due to a square-rooted arc length function made up of various different trigonometric functions. However, we can plot the speed of the curve for t greater than 0, with the speed increasing rapidly as t increases relatively slowly. To calculate the curvature, we use the following calculations, which gives the curvature and the sine curvature as follows for time t.
Next, we'll take a look at space curves. First of all, a definition. A space curve may pass through any region in three-dimensional space, a plane curve being its 2D counterpart. Some examples include a helix, where the third-dimensional axis allows the shape to spiral. In 2 dimension, the plane curve would just be a circle. Other examples being a contraspiral, Viviani's curve, and a twisted cubic. Now, space curves are related to plane curves, so there are similar features and calculations that can be used to help understand these. Similarities include the regularity of a curve, unit speed calculation, also reparameterization by unit speed, curvature, and free-note frames. These can all be calculated similarly to plane curves. In addition to this, in space curves, there is torsion and a new curvature equation, as shown in the image. When calculated, these can help us to visualize the shape of the space curve, and so when compared with the curvature of the plane curve, which also can help us visualize the shape of the plane curve, then we can see how they relate geometrically. A specific example of a space curve would be this. With the equation shown above, the image beneath could be interpreted from calculations on curvature and torsion. Specifically, the calculations show that this space curve, similarly to the plane curve, is only regular when t is not 0. It could also not be reparameterized with unit speed explicitly. Using the new equation for curvature and torsion, those could be calculated too, torsion specifically helping show how much the space curve departs from being planar. Here is shown the geometric comparison. The xy plane is the same for both space and plane curves. This means the plane curve is the 2D projection of the 3D space curve, with only variance in the z-axis. Looking from above, they would look the same. Below in the image is the space curve z-axis equation, which shows how it leaves the xy plane.
Finally, we're going to explore surfaces. By our geometric intuition, a surface looks locally like a bent piece of paper. However, we would like to formalise this. We can look at curvature, as we have done with curves, to understand their geometric forms, but informally we already have an understanding of what surfaces look like, for example a sphere, a cylinder, and a hyperbolic paraboloid. We can take our knowledge of curves and use it to relate space curves to surfaces. For a surface, S equals x of uv, the coefficients of the first fundamental form is the inner product on the tangent space of a surface in the three-dimensional Euclidean space, and are calculated from the inner products of the partial derivatives of x. So E is the inner product of xu with xu, F is the inner product of xu with xv, and G is the inner product of xv with xv. This now means we can calculate the curvature and properties of a surface, such as length and area, given in the equation shown, which, as you can see, depend on the coefficients of the first fundamental form. Now, to define the second fundamental form, we must first understand what a Gauss map is. A Gauss map N is a unit normal vector field on the surface and is given by the composition of nx with the inverse of x, where nx is the cross product of the partial derivatives xu and xv divided by the length of the cross product. The coefficients of the second fundamental form are given by E, which is the inner product of nx with the partial derivative xu, F is the inner product of nx and xuv, and G is given by the inner product nx and xvv. These can be represented by the matrix E, F, F, G. Using both sets of coefficients, we can now calculate the Gaussian curvature, which is the product of the minimum and maximum of the normal curvature, and is given by small eg minus f squared divided by capital Eg minus f squared. The mean curvature is the average of the minimum and maximum curvature, and is given by Eg minus 2ff plus Eg divided by 2 Eg minus f squared. When the mean curvature of a surface is equal to 0, it is called a minimal surface. This happens because the minimum and maximum curvatures are opposites to one another, and so the Gaussian curvature for these surfaces is always negative. To gain geometric understanding of the mean and Gaussian curvatures, we can calculate the normal and geodesic curvature of a space curve that lies on the surface. If the curve on the surface S is unit speed, and n is a Gauss map of S, then the normal curvature is given by the inner product of n composed of the space curve gamma and the double differential of gamma. And the geodesic curvature is given by the inner product of the cross product of gamma prime and n composed with gamma and gamma double prime. Now we will apply these to an example, Catalan's minimal surface. Our first step is to prove that our x of u is a surface patch. To do this, all derivatives must exist, and xu and xv must be linearly independent. As you can see, all derivatives of x exist because sine, cosine, and their hyperbolic counterparts all differentiate in cycles. Now to prove xu and xv are linearly independent, we must calculate the length of their cross product and check it's non-zero. As you can see from the graph that plots this length, xu and xv are linearly independent as the graph is always non-zero for these restrictions of u and v, and so x of u is a surface patch, and looks like this. Using the equations from before and the fact we know x of u is a surface patch, we can now calculate the coefficients of the first and second fundamental forms, as you can see from this slide. Now you know these, you can calculate the length or area of the surface patch between any 2 points in the domain, and you can also calculate the Gaussian and mean curvature, which are given by these expressions. You can also plot these to view them geometrically, as shown. For example, in the bottom right, the plot of Catalan's minimal surface, coloured to represent the mean curvature, is all red. This is because the mean curvature is a constant 0, so the colour plot is also always constant. Because our mean curvature is 0, we know that this surface is a minimal surface, hence its name. Now, due to the nature of minimal surfaces, it means that they can be created physically using a wire outline to make a soap film of a non-self-intersecting part of the surface, as you can see in these pictures of Catan's minimal surface. Thank you for watching, and we hope we gave you a good insight into the world of curves and surfaces.